All right, everybody, welcome to your fifth video lecture. This one is over integration methods. Okay, so in the first semester and even in the first part of this summer assignment, we've mostly talked about derivatives. Well, integration and anti-differentiation is just going backwards from the derivative. Okay, so to find a function whose derivative is, for instance, 2x, you might use your knowledge of derivatives to conclude that the antiderivative is x squared, because you know the derivative of x squared is in fact 2x. Okay, so that leads into the definition of an antiderivative, which you can see clearly right there. Now, if you're going to continue this discussion about 2x, you might recognize that there is more than one antiderivative of 2x, and I've listed a couple of examples here. You might have f1 of x just be x squared. The derivative of that, of course, would be 2x. You might have this function, f sub 2 of x squared minus 8. The derivative of that is also 2x, since the derivative of negative 8 is just 0. And then you might have x squared minus or plus some other constant. Okay, so the way that we kind of deal with this is by using what's called a constant of integration. And so that's what you can kind of see right here, that we're going to add on to any what is called an indefinite integral. So we'll talk about definite integrals in a later lecture, but this lecture will be all about indefinite integration. Okay, so here are the basic derivative or integration rules that you should have memorized. The differentiation formulas are all here on the left, and then the integration formula is here on the right. So the idea is an integral is just going backwards from the derivative. So just for example, you might look, for instance, at this one. Okay, the derivative of sine is cosine, which means that the antiderivative of cosine x dx is sine x and then plus some constant c. Please make sure that you don't forget about this plus c whenever you're taking an indefinite integral. Okay, so make sure that you have all of those memorized. If you have the derivative rules memorized, then it shouldn't be real hard to get the integration rules memorized as well. Now, the reason I'm scrolling back up here is because I want to alert your attention to one of the most important antiderivative rules, and this is really the one that you focused on the most in your pre-calc class, and that's the power rule. Okay, so remember, to take the derivative of a power, you're going to move the exponent into the front and then subtract 1 from the exponent. In order to take the antiderivative of a power, you're going to increase the exponent by 1 and then divide by the new exponent. So that's the power rule for integration. Okay, so let's go down here and see if we can utilize the power rule. So the first problem in example 1 says the integral of 3x dx. Okay, well, I know that the exponent on that x is a 1. Even though it's not there, it's an understood 1. And so if I'm going to use the power rule here, I'm going to increase that exponent by 1 and then divide by the new exponent. Now, if the constants could be simplified at all, I would go ahead and do that, but in this case, 3 over 2 is already simplified, and so all I really need to do is add my plus c so that I get the final answer. Okay, in example B, we have the integral of 1 over x cubed dx. Now, very similar to derivatives, if that x is in the denominator, I have to rewrite it using algebra in order to be able to use the power rule. So since that x cubed is in the denominator, I'm going to rewrite it as the integral of x to the negative 3 dx. Okay, once I do that, now I'm able to use the power rule. So I increase the exponent by 1. If I increase negative 3 by 1, it becomes a negative 2. And then I'm going to divide by the new exponent, which is negative 2. And then don't forget my plus c. So the way that I would probably write this is negative 1 over x squared plus c. So just moving the x to the negative 2 to the denominator, and then that leaves just a 1 in the numerator, and then I can't forget about my 2. That is right here. So negative 1 over 2x squared. And the nice thing about these problems is that you can take the derivative to check your answer. So like, for instance, over here, if this was, let's say, y, then y prime would be equal to 3 halves times 2x and so that would be 3x, which is what we started with back up here. Okay, example C, we have the integral of the square root of x. In order to be able to use the power rule, I'm going to rewrite that as x to the 1/2 power. Okay, so just remember from algebra that the square root of x means x to the 1/2. Okay, so using the power rule, we're going to increase 1/2 by 1, so that is going to give us 3/2, and then divide by the new exponent, which is 3/2, plus c. But anytime I divide by a fraction, that's really multiplying by the reciprocal. So this is going to be 2/3 x to the 3/2, and then don't forget plus c. Okay, example D, we have 2 sine of x. Now what I'm able to do with that constant, as we're going to find out in the next lecture, is I can move that constant into the front of the integral sign. I can't do that with any variables, but I can definitely do it with constants. Okay, so if I look back at my rules, the antiderivative of sine of x is negative cosine of x. And so our answer here is going to be negative 2 cosine of x plus c. Okay, in example E, we have the integral of 3 over x dx. So this is going to be rewritten as the integral of 3x to the minus 1 dx so that I can actually try to use the power rule. Now the reason I said try and not actually use the power rule is because notice if I increase the exponent by 1, what does it become? It becomes a 0. Well then the next step would be to divide by the new exponent, which would be dividing by 0. I cannot do that. And so what I want you to recognize back over here on this page is that for this rule, the natural log rule down here at the bottom, this can also be written as the integral of x to the negative 1 dx. And so anytime you see that raised to the negative 1, you're going to think that's the natural log rule. Okay, so the antiderivative here is going to be 3 natural log of the absolute value of x plus c. Okay, example F, we have the integral of just dx. Well, another way to think about that is just the integral of 1 dx. And so if you think, okay, well, what is a function whose derivative is equal to 1? That, of course, would just be x. So the answer here would just be x plus c. Okay, so don't get confused by that one. It's not meant to be confusing. We just need to do one like that so that you can see how to handle that. Okay, G and H are integrals of a sum or a product. This is really not any different than what we've done in the first couple of examples. We're just going to take the antiderivative one term at a time. Okay, so for example G, we have the integral of x first, and so that's going to be x to the second power divided by 2. So increase the exponent by 1 and divide by the new exponent. And then the antiderivative of 2 is just 2x plus c. Now if you wanted to rewrite that as 1/2 x squared plus 2x plus c, certainly that would be perfectly fine. If you wanted to leave it like this, that would also be perfectly fine. It's really just about what does the answer choice look like that you're trying to find. Okay, and then example H, very similar to example G, so we're going to increase the exponent by 1. That's going to become a 5, and then divide by the new exponent, minus 5x cubed over 3 plus 1/2 x squared plus c. Okay, so again, just an application of the power rule, increasing the exponent by 1 and then dividing by the new exponent. Okay, in example I, we have a fraction. And so whenever we have a fraction with x's in the numerator and denominator, we're going to have to split through the numerator in order to be able to find that antiderivative. So this is going to become the integral of x over square root of x, but instead of square root of x, I'm going to write that as x to the 1/2 plus 1 over x to the 1/2. Okay, so just splitting through the numerator there so that I can set up using the power rule. Okay, well still without using the power rule, we're going to simplify. So x over x to the 1/2 is x to the 1/2 plus 1 over x to the 1/2 is x to the negative 1/2 dx. Okay, now I have done enough algebra in order for me to be able to use the power rule. So I bump up the exponent by 1, that's going to say x to the 3/2, and then divided by 3/2 is the same thing as times 2/3. And then plus, if I bump up negative 1/2 by 1, that's going to become positive 1/2. Dividing by 1/2 is the same thing as multiplying by 2. And then don't forget plus c. Okay, very similar in J, so we're going to move that square root of x up to the numerator. It's going to become 2x to the negative 1/2 dx. And then increase the exponent by 1. That's going to become an x to the positive 1/2, and then divided by 1/2 is times 2 plus c, which is going to give me 4 square root of x plus c. Okay, it would have been okay to leave it to the 1/2 power, but again, I want you to kind of see the different ways that the answer can be written, because you never know what the answer choices might look like. Okay, in K, we have the integral of t squared plus 1, but then all squared dt. What we have to do in this case is go ahead and square out the t squared plus 1. Okay, so if we think about this as being t squared plus 1 multiplied by t squared plus 1 dt, then that means that this is going to equal the integral of t to the 4th plus, we have 1t squared here and another t squared there, so that's a total of 2t squared, and then 1 times 1 is going to give me 1. Okay, so I have to multiply all of that out so that I can now use the power rule. So if I use the power rule, this is going to say 1/5 t to the 5th plus 2/3 t cubed plus t plus c. Okay, example L is very similar to example I, and so I'm going to again split through the numerator so that I have x cubed over x squared plus 3 over x squared dx. Okay, and then simplifying that into a format that I need in order to use the power rule, we're going to have the integral of x plus 3x to the negative 2 dx. And now I am able to use the power rule. So the antiderivative of x is just 1/2 x squared, and then the antiderivative of 3x to the negative 2 is going to be x to the negative 1. Don't forget about the 3 that's here. And then divided by negative 1 is just going to change that into a minus sign in between those terms. And then plus c, which of course could be rewritten if you wanted to as 1/2 x squared minus 3 over x plus c. Now again, I'm not going to get too caught up in how you write the final answer, because it's all going to depend on what the answer choices look like. But you need to be able to recognize that certain things mean the same thing. So what I mean by that is you need to be able to recognize 3x to the negative 1 and 3 over x are really saying the same thing, just in a different form. Okay, examples M and N. So in example M, we're going to have to distribute that cube root of x before we get going, because we cannot take the integral of a product. We'll actually learn in BC how to take the integral of a product, but that is not this type of a problem. So the first thing I'm going to do is I'm going to distribute the x to the 1/3 power. So I know I can think of this as being x to the 1/3. When I distribute that x to the 1/3 with that x to the first, I'm going to add their exponents. And so if I add 1/3 and 1, I'm going to get 4/3. And then minus 4x to the 1/3 dx. Now I'm ready to use the power rule, so this is going to be x to the 4/3 plus 1 is really 7/3, divided by 7/3 is the same thing as times 3 over 7. Okay, minus 4, and then x to the 1/3 plus 1, well, that's going to end up being 4/3, and then divided by 4/3 is the same thing as times 3 over 4 plus c. And so if I were to clean up that middle term, my final answer is going to be 3/7 x to the 7/3 minus 3 x to the 4/3 plus c. Okay, example N, we have the cosine of 3x. Well, if I look back at my rules, I know the antiderivative of cosine is sine. So that would lead me to believe that the antiderivative here is sine of 3x plus c. Okay, so I'm going to leave that there for just a minute and conjecture that that's the answer, and then I'm going to show you why it's not the answer. Okay, so here's why it is not the answer. If you were to retake the derivative of that answer that I'm saying is not the answer, then here's what you would get. The derivative of sine of 3x is really equal to 3 cosine of 3x. But we don't have a 3 in the original problem. It's not there. So what we're going to do is we're going to kind of just put it in there, okay, like this. So I'm just rewriting the original problem, the integral of 3 cosine 3x. But in order to do that, I've got to make sure I don't change the problem. So if I multiply by 3, I've got to also divide by 3 or multiply by 1/3. And so now the antiderivative of this piece is this, and because of this 1/3 that's in the front, we've got to have a 1/3 in front of our answer. Okay, so our final answer altogether is going to be 1/3 the sine of 3x plus c. And now if you were to take the derivative of this, you would get back what we originally started with. So you've got to be very careful to pay attention. Is there a constant there that you need to kind of account for? Okay, the next thing we want to talk about is integration by substitution. So we'll kind of talk about this more in future lectures as well, but the idea behind integration by substitution is to sort of undo the chain rule. So it's in essence a way of reversing the chain rule for taking derivatives. Okay, so example 2, we want to find the antiderivative, which basically means to find the integral. Okay, so when I'm doing a u substitution, what I'm looking for is a function inside of a function. So I'm going to write that down. The first thing whoops, maybe I should probably write with the pen. The first thing I'm looking for is a function inside of another. That's the first thing I'm after. Okay. The second thing that I'm looking for is the derivative of my choice somewhere in the problem? Is the derivative somewhere in the problem? If it's not a good choice of u, and I need to try something else. If it is in the problem, I've chosen the correct u, and I can proceed with the u substitution. Okay, so if we look at example 2a here, we have the integral of 2x times x squared plus 1 squared dx. And so the reason I know that this is a u substitution problem is because I see a function inside of another function. Okay, so there is the function that is inside of another function. It's the x squared plus 1 inside of a square. So I'm going to choose u to be equal to the thing that is inside the square. That would be the x squared plus 1. I'm going to then figure out what is du. Well, the derivative of u is 2x and then dx. Here's what I see as far as the problem goes. I see that I have 2x here and dx there. And so that's how I know I have made a good choice for u. So now what I'm going to do is I'm going to substitute so that I can actually find this antiderivative. So this is going to be the integral. The stuff in yellow here is going to get replaced by u, because notice that u is equal to the x squared plus 1. So anywhere I see x squared plus 1, I'm going to put a u, and then it's u squared. Then the stuff in the blue, 2x dx, is going to get replaced by du. So I'm just going to put du down here at the end. Well, now I have the integral of u squared du. I know how to find that antiderivative. It's just using the power rule. So that's going to be 1/3 u cubed plus c. The last thing I want to do is I want to plug back in what u actually is in terms of x. And so my final answer is going to be 1/3 x squared plus 1 cubed plus c. Okay, and that right there is going to be the final answer. Again, as always, if you want to check your answer, just take the derivative and make sure that you end up with what you started. Okay, I'm going to erase these notes that I made over here, so hopefully you're able to copy those down. If not, then you can obviously rewind the video. Okay, in part B, example B here, I'm again looking for a function that is inside of another. Sometimes that's going to be in the denominator, sometimes it's going to be under a square root, sometimes it's going to be in parentheses, sometimes it's going to be an exponent. So that last one that I just said, exponent, is obviously the case here. So u is going to equal to 5x. That means that du is equal to 5 dx. Well, I notice that I have 5 and dx in the problem, and so that's how I know I made a good choice for u. So this is going to be the integral of e to the u du. Well, the antiderivative of e to the u, if you go back to your other page, is just e to the u plus c. And so now if I resubstitute back in what u is, our final answer is going to be e to the 5x plus c. Okay, and again, you can just take the derivative of that. If you're not convinced that that's the answer, make sure that you end up with 5e to the 5x as your answer whenever you take the derivative. Now, this paragraph towards the bottom of page 5 of the notes is basically just talking about the fact that in example 2, the constant that we needed was in the problem already. That is not always going to happen, and in fact, it's usually not going to happen. And so in the next page of the notes, on page 6, we're going to show you how to work problems where that constant may or may not be there. Okay, so example 3, find the antiderivative and then integrate, and really that's talking about the same thing. Okay, so example A, this is very similar to the first example of example 2, except this time we're missing the 2 that's in the front. So we'll talk about how to deal with that. And I just noticed that there's a typo on these notes, so I'm going to put in that squared there so that that's on there, and then I'll correct that on your notes on my web page. Okay, so again, I'm looking for a function inside of another function, and so in this case, that would again be the x squared plus 1, since that is inside of a square. And then I'm going to take the derivative of that. So the du is going to be 2x dx. Okay, well, what I notice is that I have the x dx part, so the x dx part is here and here, but what I'm missing is a 2. And so what I'm going to do with this equation right here is I'm going to solve for what I have. I have x dx, and so I'm going to solve for it and make it say 1/2 du is equal to x dx. And so now for that x dx, we're going to substitute in 1/2 du. So this is going to say 1/2 the integral. Du is going to be down here at the end, and then this part in yellow, okay, just like it was on example 2, that yellow is going to get replaced by our u. So this is going to say u squared. Okay, so now we take our antiderivative. So this is going to be 1/2. The antiderivative of u squared is 1/3 u cubed plus c. If I want to simplify that, that's going to be 1/6 u cubed plus c. And now I want to plug back in what u was. If you look back up there, u is equal to x squared plus 1. So this is going to be 1/6 times x squared plus 1 cubed plus c. Okay, and again, I'm going to reiterate this a couple of times. You can take the derivative in order to check whether or not you did it correctly. Okay, example B, I'm looking for a function inside of another function, and I'm hoping that the function that I choose has its derivative somewhere in the problem up to a constant. Okay, well, hopefully, if you look at this, you're able to recognize that our u is going to be x cubed minus 2, since that's the function that is inside of a square root. That means that du is going to be 3x squared dx, but I don't have 3x squared dx in the problem. All I have in the problem is the x squared dx. I have it here and there. So in order to compensate for that, we need to solve for x squared dx, which just means we need to divide both sides by 3. So that's going to say 1/3 du is going to equal to x squared dx. Okay, so now for everything that I see in blue there in the original problem, we're going to replace that with 1/3 du. Okay, so this is going to equal to 1/3. Integral sign just stays an integral sign. And then du, I'm going to draw a little line here so that things kind of stay separate. And then for the yellow piece, let me get the yellow going here. For this piece under here, that's going to get replaced with u. But that is underneath the square root, and so I'm going to rewrite that as u to the 1/2 power. Okay, once I get that done, now I need to take the antiderivative of u to the 1/2. So that's going to be 1/3 multiplied by 2/3 u to the 3/2 plus c. And then the final thing is to get the constant cleaned up and then resubstitute back in what u was equal to. So that's going to say 2/9 multiplied by x cubed minus 2 to the 3/2 plus c. And that will be our final answer for example B there. Okay, example C, we have the integral of x over x squared plus 9. So again, we're looking for a function inside of another function whose derivative is somewhere in the problem up to a constant. Okay, so if you take a second to think about this, hopefully you recognize that x squared plus 9 should be our choice for u. The reason for that is because du is 2x dx, and what I notice is that I have the variable part of du in the problem, and I'm just missing the 2. Okay, so I'm going to go ahead and solve this equation for x dx. That's going to say 1/2 du is equal to x dx. And now all of the blue stuff in the problem is going to be taken out and replaced with 1/2 du. So this is going to be 1/2 the integral of du. Okay, then the part that's underneath the square root here, that's going to get replaced by u. So what we're going to end up having is 1 over the square root of u. Now I can't take the antiderivative of 1 over the square root of u. I've got to rewrite that in a format that makes it easy to take the antiderivative. So I'm going to rewrite it as u. Since it's in the denominator, I know it's going to have a negative exponent, and since it's a square root, I know that the exponent is going to be the negative 1/2 power. Okay, so this is going to end up being 1/2. Now I'm going to take the antiderivative of u to the negative half, which is going to be u to the positive 1/2, divided by a half, which is really times 2, plus c. And so what ends up happening is that 1/2 and 2 cancel out, and I get u to the 1/2 plus c. So I'm going to go ahead and rewrite what u was. U was x squared plus 9 to the 1/2 plus c, or another way I could write that is the square root of x squared plus 9 plus c. Okay, example D. We have the integral of x plus 1 over x squared plus 2x. Well, again, I mentioned earlier that your choice for u is typically going to be in parentheses, in an exponent, under a square root, and possibly in a denominator. So if you choose the denominator here, that would be x squared plus 2x. That means that du is equal to 2x plus 2 dx. Well, that's got to be somewhere in the problem, but up to a constant. Well, notice that 2x plus 2 can be factored. So I could factor out a 2 from that, and that would leave me with x plus 1 multiplied by dx. That is what I see there in the problem. Okay, so if I get the blue going here, the x plus 1 dx, that's going to get replaced after we come down here and solve our equation for what we have. That's going to be du over 2 is equal to x plus 1 dx. Okay, so this is going to be the integral. The 1/2 is going to go in the front. The du will go at the end. And then I'm going to replace this stuff that's in the yellow. So this stuff, whoops, sorry about that. This stuff in the yellow is going to get replaced by u. Well, the x squared plus 2x is in the denominator. So this really ends up being 1 over u. Okay, well, I need you to get used to recognizing that 1 over u du, the antiderivative of that is natural log. So this is going to be 1/2 the natural log of the absolute value of u plus c. And just to kind of reiterate why that is, remember that this is u to the negative 1. And if I try to increase the exponent by 1 and divide, I can't do that because I'd be dividing by 0. And that is how you should think about why you need to use the log rule as opposed to the power rule. Okay, so our final answer here is going to be 1/2 the natural log of the absolute value of x squared plus 2x, and then plus our c. Okay, last two examples here, and then we're done. So we have the integral of x cosine of x squared dx. Okay, so u is going to equal to some function that is inside of another function whose derivative is somewhere in the problem, except for maybe a constant. So in this case, our u is going to be x squared, which means that our du is going to be 2x dx. And again, notice that I have x and dx in the problem. I'm just missing the 2. So I'm going to go ahead and divide that to the other side so that x dx is solved for. And so what I'm going to end up having is 1/2 the integral of du. And then this rest of this stuff here is going to get replaced by cosine of u. Okay, remember that this x squared is now equal to our u, and so that's why I put in u instead of x squared. Okay, well, the antiderivative rule for cosine of u is sine of u plus c, and if I replace what u was, I'm going to be done. So 1/2 sine of x squared plus c. Okay, so again, take the derivative of your answer, make sure you get the same thing. Okay, last problem, e to the 4x. This is very similar to example 2b. So again, u is going to equal to the exponent, which is 4x. That means that du is equal to 4 dx, but because we don't have a 4 in the problem, we're going to need to divide by 4 on both sides so that dx gets replaced with 1/4 du. So 1/4 the integral of du, and then that's just e to the u left over. And the antiderivative of e to the u is just e to the u. So this is 1/4 e to the 4x plus c. Okay, that was a lot of examples, so if there's anything that you don't understand about something, please contact me and get in touch with me and ask me questions about what you do not understand. Good luck to you guys, and hope the assignment goes well.